Welcome to What is a Wave Part 3. Today we're going to be talking about two types of wave graphs. We have displacement and position, XY graphs, and displacement and time graphs, which is T and X. So our first graph is going to be on our standard XY axis, where X denotes your displacement and Y is your position. M's are reminding us that our units are in meters because both of these are distance measurements. And our wave is going to look something like this. You'll often see an arrow showing that with a V saying that it's moving this direction. On this graph, we can label our amplitude. We just use a capital A for amplitude. It's in units of meters, and it is basically the height of each wave. You can also measure it from down here. That's a negative amplitude, and that's the depth of your trough. We also have on this graph a wavelength. We can measure the length of each wave pattern. So you see we start at one point and we come down to the exact same point on the next waveform. That's going to be a wavelength. So wavelength, which we use lambda for. It's in units of meters. That's lambda, the Greek letter. And this is the length of a wave. We can also measure it from peak to peak, or from like here to here, just the same spot on the waveform to the next waveform. All right, so on our displacement versus time graphs, we have our axes, but this now is time, T, and it's in units of seconds, and this is X in units of meters. So we have displacement over time. And our graph is going to look like this. So it looks essentially the same as that graph does. The way we get this graph is if we draw X equals 0. This is our pendulum. If we release the pendulum at some point here, it's going to fall through here and come to some point over here, right? And then once it hits here, it's going to decrease, so it has a velocity of 0. And then it's going to come back over, and it's going to hit velocity of 0 again, and then it's going to keep swinging back and forth. You can see we'll have a V max right here when it crosses the x-axis. This is our axis. So now over here, this is our x-axis, even though we call it t, but it's still the x-axis. So when x is 0, we've got some amplitude. That's what we have right here. So this is still our amplitude. And now we release the pendulum, and we come here. This is where we're crossing the x-axis, right here. That's where we had our V max. And then we keep swinging, and we hit our negative amplitude down here. Velocity is 0 here. And then we come back, we hit our V max. And then V equals 0. And we're just going to keep swinging. So this graph shows you how this pendulum moves over time. So we still have our amplitude on this graph. But now, if we measure between trough to trough or peak to peak, we're not going to be measuring a unit of length like we were over here. Instead, we're going to be measuring a unit of time. So if we measure from here to here, we get something in time because we're measuring something on the x-axis, which is our time axis. We call that T, capital T for period, units of seconds, and it's the time for one wavelength. One wavelength would be us going like that. That's one wavelength from the starting position back to the starting position. So if we measure from starting position, we say that was over here. And then we go back to starting position. That was one wavelength. So this distance is one wavelength. And that was the time for one wavelength. We also have frequency. We just use lowercase f for frequency. It is in units of 1/seconds. Sometimes you'll see it written as seconds to the -1 or inverse seconds. It's also written as hertz. This is equal to 1 over the period. So our frequency is essentially how many wavelengths came through in 1 second. So for measuring period, we set the length to be one wavelength, and we measured whatever time that would be. When we're measuring frequency, we say we've got 1 second, how many wavelengths came through. Lastly, we have velocity. Velocity is equal to delta x over delta t. That is delta. It's a Greek letter. It means change in. Velocity is a slope on this graph. So it's the change in our x over the change in our y. So if we were calculating the slope right here, we would say, okay, so we went from x equals 0 to x equals some other number and divided by the t value for here and here. So when we're doing this for waves, we will often write this as lambda f or lambda over period. These two are equivalent if you just plug in f equals 1/t.